If a and b are integers and a plus b is 2005, what is the least possible value of the absolute value of a minus b? A minus b absolute value. Well, we all know that absolute value of anything is going to be positive, but it could also be 0. So greater than or equal to 0. Now they want the least possible value, so the least possible value of this is 0. So let's see what happens if we set it equal to 0. If that is true, that means a minus b is 0. That means a equals b. If a equals b, let's plug it back into there and see what happens. A plus b is 2005, then becomes b plus b is 2005, and that means 2b is 2005, and therefore b would be half of that, so 1002.5, I believe. Well, unfortunately, that's not an integer, so that failed. That's not a problem. We can go to the next one. 0 didn't work, so let's try the next possible value. Since they're integers, the next possible difference in terms of the least possible is 1. So let's see what happens if we set it equal to 1. That means a minus b is 1. It could be the other way around. The b minus a is 1, but we'll just try this one first. That means a equals b plus 1. Going back to this original equation, that means that b plus 1 plus b is 2005, and that means that 2b is 2004, and therefore b is 1002. And therefore, a would be 1003. And therefore, this works. A minus b would therefore be 1003 minus 1002, absolute value, which is just 1. So the least value is 1. What is the only pair of non-negative integers mn for which 3 to the power of n minus 1 is equal to 2 to the power of n plus 1? All right, so I think this is just done by inspection. I don't think there's any formula. So let's see. Let's try. They're non-negative integers. Non-negative. So it could be 0. If m is 0, let's see what do we get. We get 3 to the power of 0 minus 1 is 2 to the power of n plus 1. That's 1 minus 1, 0, 2 to the n plus 1. Okay, so this falls apart because this can never be negative 1 since these are non-negative. Okay, no problem. Let's try m equals 1. Then that becomes 3 to the power of 1 minus 1, 2 to the power of n plus 1. That's 3 minus 1, which is 2. 2 to the n plus 1. So 2 to the n is 1. And that is true if n is 0. So there we go. mn is 1, 0. And that works. This big long number will be a perfect square if one of its digits is increased by 1. What is the value of this digit? Well, I certainly am not going to do long division, but since calculators are allowed, just take that number and plug it into your calculator, just the number that they give you, and take the square root and see what you get. And when you do, you will get this number. You get 22222222221 dot dot 9999 and so on. So obviously that number is very close to 222222222, obviously. So this number, square it, and when you do, you will get the following number: 4938271603617 284. So you see, this guy and this guy are really the numbers that they're referring to in the question. So they're asking, what is the value of this digit before the increase? Well, before the increase, the number was a 3. Squares are drawn as shown on the long sides of a shaded rectangle. A diagonal of the resulting figure cuts off a 5, 12, 13 triangle from each square, as shown was the area of the shaded region. Okay. Well, if it's a square, that means this side is 12, like that. They're all 12s. And if from here to here is 5, and the whole side is 12, and that means from here to here would be 7. Got it? And then, let's see, anything else that we know? I think that's it. Well, and so therefore I have to call that x since I don't know the length of that. So I'll draw it again here just to kind of remind you what it is that I'm looking at, and I'll label it. So this side is 7, this side is 5. From here to here is 13, and from here to here is 12, and then this is x, correct? So using similar triangles, 5 over 12 is the same as 7 over 12 plus x, right? Okay, so let's work with that. Cross multiply, and we get 7 times 12, which is 84. And then we get 60 plus 5x. And therefore, that's going to be 24 as 5x. And therefore, x would be 4.8. And then the area, that shaded region area, is really just 12 times x. And then 12 times 4.8 will give you 57.6. My accurate 12-hour circular clock has 60 equally spaced minute marks, 1 at each minute. What is the first time after 12 o'clock that my clock's continuously moving hour and minute hands point directly to consecutive minute marks? All right, so a lot of explanation involved here, but some of you may not need that much, but let's see what we can do here. The minute hand, which I'll call M, the one whole way around the clock is 360 degrees, but there's 60 minutes, so each minute will move 6 degrees. Like if you go from 12 o'clock to 12:01, you've moved 6 degrees. For the hour hand, it's 360 degrees, one rotation around, but you only have 12 hours, so this time it's 30 degrees. So every time the clock moves 1 hour, you move 30 degrees. Now, you guys all know that, of course. Now, we need to give some examples to illustrate what's going on here. If you look at these two numbers, we have to sort of get a kind of a ratio. So that ratio is obviously 30 to 6, which is 5, right? So that basically means, sorry, what did I do here? Yeah, that ratio is 5. But let me see if I can explain it in like a sentence. So the hour hand lies exactly on a minute mark every 6 degrees. So I'll draw a little diagram. So let's say you're normally, when you look at a clock, you're used to seeing the numbers as the hours. So this is 1 hour, this is 2 hour, this is 3 hour, and so on, right? You guys remember that, of course. But I want to actually emphasize that it can be labeled, at least in our question, in terms of minutes. So normally we've got 1, 2, 3 as for the hours, right? But for the minutes, I want to label it. Now the minutes, there's 60 minutes. So as we showed here, each minute marker is 6 degrees. So we're going to have 1 here, 2 here, 3 here, 4 here, 5 here. So this was minute number 1, minute number 2, and so on, minute number 3. Those red lines are representing minutes. So an hour hand, let's say it's 12:06. It will move to the 1 minute marker, which is this guy right here. And that's what I'm trying to illustrate. So hopefully that makes sense. Sorry, I meant to say 12:12. Sorry about that. I meant to say 12:12, and let me explain why. I'll explain it, or at least try to explain it a little bit better. So let's say you have the clock, and it's 12:12, right? So the minute mark obviously is at the 12-minute mark. So the 12-minute mark, let's say, so we got to do this carefully here. Every 30 degrees, it's a 1 hour, but every 30 degrees, there's 5 of these guys. So Let me just see if I can draw them in 1 minute, 2 minute, 3 minute, 4 minute, 5 minutes. Okay, so let's just put a 5 there. This is minute marks, not hours. And then similarly 6, 7, 8, 9, 10. And I know this isn't drawn to scale, but you guys get the idea. 11, 12, 13, 14, 15. So at 12:12, the minute marker is at 12. But the hour marker will have gone 12 out of the 60 minutes, which is 1/5. So 1/5 from here to here, and 1/5 from here to there is this guy right here, the 1 minute mark. So the hour, let me see if I can draw it in a different color, will be pointing to the 1. So that's the hour one, and this is the minute one. So that is an example of where the hour hand lies exactly on a minute mark. So I think perhaps that further explanation made a little bit more sense. And similarly, every 12 minutes after that, if you go to 12:24, it'll be the same thing. The minute marker will move to the 2, and then the hour hand will move to the number 2, and the minute marker obviously will be pointing to the 24-minute mark, and so on. So every 12 minutes, you're going to get in a situation where the hour hand lies exactly on a minute mark. It's 6 degrees, but it's 12 minutes. So I'll put that in there, 12 minutes. So what they're asking for is when do we get to a point where they're consecutive minute markers? Like, for example, in the 12:12 example, the minute markers were 12 and 1, right? The hour hand was pointing to the 1, and the minute marker obviously was pointing to the 12. Now, the number 1 and the number 12 are not consecutive numbers. So you just got to keep going 12-minute increments, 12:24, 12:36, and then see. And then finally, when you get to 2:12, you will see a situation where this happens. And so let's illustrate that one. So 2:12, obviously, the hour hand will be pointing to the 2. Obvious. Well, actually, no. Let's wait here. Let's just do the minute marker first, because that's the easiest. Hold on. So the 12-minute marker is, let's see here. Let's do this carefully. Let's label it in minutes. So this would be the 5-minute marker. This is the 10-minute marker, this guy. And the 12-minute marker is somewhere here. So that's the 12-minute marker. Okay, that takes care of that. But then where is the hour? The hour guy is the hour marker, hour hand. It is pointing, let's see here, we can figure it out, 12 over 60, so that would be 1/5. So basically 1/5 of the way between 2 and 3, if you look at it from the perspective of hour markers. And 1/5 of the way between 2 and 3 is the 11th, this guy, the 11th minute marker. So the hour hand will be pointing to the 11. So therefore, since 11 and 12 are consecutive numbers, this is the first time where both the hour and minute hand point to consecutive minute marks. What are all integers k for which x squared plus kx plus k plus 17 is equal to 0 has integral roots? X squared plus kx plus k plus 17 is equal to 0. All right. Well, there's several ways of doing this. I'm just going to use Vietas. You guys remember Vietas. If you use this equation, the sum of the roots, you can call them whatever you want. Let's say the roots are a and b. So the sum of the roots would be minus k over 1, which is just minus k, using Vietas' formula. And then the product of the roots, using Vietas, and in our case our roots are designated AB, would be k plus 17 over 1, which is of course just k plus 17. All right, that takes care of that. Now we have to somehow come up with some correlation. If I add up everything, a plus b plus ab, that gives you minus k plus 17. So that means that a plus b plus ab is just 17. And then if I factor out a b, I'm going to get 1 plus a. And then, can I do anything here? I think I can isolate for a, perhaps. So how do I do that? Let me just see if I did this right. It doesn't really matter. I mean, it doesn't really matter, I think, how you factor it, but I think it helps if I probably factor out an a and then 1 plus b and then b. That probably might make it a little bit easier, because then this would be 17 minus b over 1 plus b is a. Okay, I think that's a little bit more promising. Not entirely sure what direction I was going in before, but now this one, we're going to break this up into minus 1 minus b plus 18 over 1 plus b. And then therefore that becomes minus 1 minus b over 1 plus b plus 18 over 1 plus b. And that is basically negative 1 plus 18 over 1 plus b. And that's a. Now at this point, everything is an integer, right? K is an integer and the roots are integers. So that means a is an integer. And the only way a can be an integer is if this guy is an integer. And the only way that is an integer is if 1 plus b is a divisor of 18. So that means it could be plus or minus 18, plus or minus 9, plus or minus 6, plus or minus 3, plus or minus 2, and plus or minus 1. Correct? So that will allow me to get values for b. Like, for example, if it was 18, b would be 17, and then so on. And then for each value of b, you can plug it back into here and get a value for a. So if b is 17, that would mean a would be, let's see here, b is 17, that would be 0. And then you can go back to the original equation and plug it in to get the value for k. So if b is 17, the original equation is x squared plus kx plus k plus 17. Let's just use b is 17, and remember b represents a root. So that would be 17 squared plus 17k plus k plus 17. So that is, I don't think that actually gives you hold on, let me see here. Let's just do this. It does. It does give an integer value. For some reason I thought it wouldn't. Okay, so k equals minus 17. And similarly, you kind of just keep going with this whole list and keep doing the same thing. And when you do, you'll get the following values. Minus 17 we just got, we get a minus 9, you get a minus 7, you'll get an 11, a 13, and a 21. Those are the values of k that you're going to get.